Okay, welcome back. So we'll continue our discussion on this thermal treatment, and my goal is to kind of complete this discussion on thermal treatment during this particular module. So as we know, if you remember from the last video, towards the end we were looking at some examples of how this waste to energy thermal treatment is being used around the world. European Union is kind of leading the pack in terms of having especially Western European countries, as you can see in this particular in this particular slide, in this particular like a bar chart, or here on the left hand side. In this the middle one, the magenta color, is the incineration. So as you can see on the left hand side, we see more and more of incineration happening, and the blue one is your recycle. So more recycles are also happening and more incineration is also happening. And then the light yellow color that you see is the landfill. So as you go from the Western European countries to the Eastern European countries, you see more and more landfillings taking place over there. So but again, waste to energy is very popular in Western European countries. It's popular in other countries as well. We have especially in South Korea, in Japan, and you'll see some examples, and they are being built. Some of these have been built in a very fancy way, as you can see on this particular. I showed you this picture in the last video as well. I just wanted to I recapped few slides just so we can continue this discussion. So here a small facility, not big, 200 tons per day in UK. Then we have in France, in Lille, France. So this is another waste to energy plant very close to a agricultural area. So then we have Korslo, Germany, another waste to energy plant over there. Paris, France, you can see another waste to energy, 350 tons per day. Not a huge plant, but pretty good. And then this one is what we were looking at towards the end yesterday on the previous video. It's in Vienna, Austria, and I told you that if you've been to that area for whatever purpose it could be, make some time to go visit this facility. You will really enjoy that. It has a waste to energy museum as well, and as you hear in the if you see this is actually the chimney. That's what you are looking at, is a chimney, and it goes taller. The picture is kind of cut at that particular point. So that's the chimney where the air emission is stacked. So you can think it's made very beautiful. It looks very nice. It's kind of in the very close to residential neighborhood, but people appreciate this stuff, and then the air pollution is so less. It's actually the air coming out of is pretty clean, so it meets all the air quality standard. Then there was in Japan, as I said earlier, 90% of the solid waste is combusted. With 90% of the solid waste is combusted, mostly with energy recovery. So in Japan they are doing it. 2,300 combustion facility in Japan. So think about that tiny country has 2,300 combustion facility, and in India we are still probably is less than 10. So again, but that doesn't mean I should not have said that, because what happens is people take it literally. Like, since Japan has so many, why don't we build so many? First of all, we need to make sure whether our waste will really work in this combustion facility. We have to work on the collection system. We have to make sure our waste doesn't get mixed with construction demolition, the street sweeping, lots of moisture, and those things actually becomes a detrimental to the success of waste to energy plant, because the your energy balance doesn't work. You will not be able to produce a good amount of energy coming out of it. If it doesn't come out, if you end up again, it all boils down to the economic viability of the plant. And in terms of the economic viability, the input material, say if the coal is bad, in Indian context, we always hear about that our coal is very bad, that's why we need to import from Australia and other countries. Similarly, if our waste to, like a municipal solid waste feed going to these waste to energy facility, if that's bad, then we need to make sure that it's of good quality. When I say good quality, it should be of good calorific value, and it can be done. The thing is that what we need to do is we need to make sure that municipal solid waste incinerator only gets municipal solid waste, and specifically if we can remove this wet and dry. As per Municipal Solid Waste Management Rules 2016, we have to do this separation of wet and dry. So that's That's actually number one. If you want to take like the number one message out of this course, at the end of this course, it's wherever you go, whether you are in industry, whether you are in you are working for State Pollution Control Board, Central Pollution Control Board, Swachh Bharat Mission Directorate, whichever position you are in right now, if you can advocate for wet and dry separate collection, if we do that in the country, throughout the country, especially in the urban areas, we will actually solve half of the waste management problem. Our half of the waste management problem is right there in the collection. Technology we have in the country. We don't have to worry about the technology, but if we can do this wet and dry separation, take this dry waste, do waste to energy, take this dry waste, try to take out some of the recyclables which is still there. So those things can be done. Wet waste, urban centers, probably anaerobic digester is better than composting because of the land requirement and all that. An anaerobic digester, you can generate some energy and you can use that energy in those urban centers for some and then you don't even have to put it in the grid. It could be just a local system. And then you have the sludge from anaerobic digester gets mixed with other agricultural and other waste which cannot be treated in an anaerobic digester kind of system. So that could be composted. So the area required for composting will be much less. Again, if we take entire food waste of say Delhi or Bombay or Calcutta and Chennai and try to make a huge compost facility out of there, if it works, it's great. But first of all, we need to see whether the market is there. We have to do a very thorough market analysis and honest about it. If it's not there, it's not there. We cannot really create the market. We can, but with the regulation has to be in place and there is a lot of things goes in there. But if the market is not there for compost, just making compost because it sounds good to make compost, I don't think that's going to work on a longer period of time. Initially, it may work when the government is subsidizing it, but that compost somebody has to buy. The compost plants has to stand on its own feet. And that's why I say that in the urban, especially in the urban, highly urbanized area, let's take the food waste, do the anaerobic digestion, and then sludge from anaerobic digestion mixed with other waste which could not be anaerobically digested, and do compost for that. So those things. So in terms of waste to energy, again, waste to energy for the dry waste to energy could be a solution. We have to look at the calorific value. We have to make sure if we have low calorific value, what kind of technology will work with this low calorific value. So here they have for example, in Japan, what they have very strict land disposal guideline. No raw waste or no ash without stabilization, it can go to the landfill. And I said 90% of the waste in Japan is combusted. 90%, 2,300 combustion facility, 23 waste to energy facility only in Tokyo. And then they have very high standards in terms of air quality. So high standards for social integration and environmental performance. It's a double of typical North American and European cost. But Japanese people are ready to pay for it. So if they are ready to pay they are ready to pay either in the form of taxes or fees or whatever, and it's working over there. So it all boils down to everything like economics has to be strong. If economics is not as strong, the thing is not going to survive for a long period of time. Here they have a waste to energy plant, and then they have a sludge burning plant side to side. They have a waste to energy plant. Let's go back. Yeah, so they have a waste to energy plant, and we have waste to energy and the sludge burning plant. So what they are doing is they are generating from the waste to energy plant. It's heat is generated. The heat is used to dry the sludge. Then dried sludge has good calorific value, so that can even go back to the waste to energy plant again. So it's kind of win-win for both. So they have, as you know, sludge has a lot of moisture. So sludge, the moisture has to be removed. We have talked about that already because of the latent heat of vaporization. So we can do this waste to energy, then take the heat, use it for sludge, especially the heat which could not be captured. So it's like a waste heat that if you can capture those heat and take it to the sludge burning sludge facility where you have dry the sludge and then use that dried sludge as a feed for the waste to energy plant as well. So there are some miscellaneous issues associated with waste to energy system. First of all, diversity of waste. So again, waste to energy system it's a plant. It's any plant, any process requires at some sort of consistency in the feed. So if you think about the coal, if you have too much variety of coal, if you have think about you have a process in there. Just in a black, like here we are thinking about this, I put a red box, and then we have a feed coming into the system, and there is some reactions going out, and then we will have some products coming out of that. So this reaction which is going in there, if we can provide a constant feed, if the feed that is going into the system is of consistency, it's of same consistent kind of quality, then the process works much better. The efficiency of the process is much better. So that's what we are trying to do. So because of the diversity of the waste, it requires that better incineration controls are used to ensure complete combustion. So since the waste is so diverse, we have to make sure that we have a better control on that. Then delivering constant waste to the combustion chamber. Make the waste, constant waste would be going into the combustion chamber. Maintaining sufficient temperature, we talked about that. You cannot start and stop the operation. Once the operation is on, it's on. And replacement of the refractory material is expensive. Once it's costly to, and then it does compete against 3 R's for input material, because you have reduce, reuse, recycle. If you do the reduce, reuse, recycle for most of the material, the common sense says that it will be a problem, that if you do a lot of reduce, lot of reuse, lot of recycle, since those material will not end up in a waste to energy plant, and then our combustible the heat value will go down. So in same material, so the same material which is useful from recycling is also combustible, same has a good calorific value. But what we have seen from the practical experience from the Western European countries, from the Japan, Korea and other places, it said that we do not really capture all the recyclable material. It's because of the mixture with non-recyclables. And we have in the Western European experience have shown that combination of recycling and incineration is a more complete and integrated waste management approach. And as I showed you that the first slide that we looked into this video, as you saw from the Western European countries, they have high recycling as at the same time high combustion facilities, like high percentage of waste going into combustion facilities as well. So then the other thing is that we have to look at in terms of the effectiveness of incinerator. Effectiveness means essentially from the air pollution control point. One of the major thing we worry about in terms of which gets a lot of attention from environmentalist standpoint is the air pollution. Air pollution coming out of these waste incinerator, whether we are able to control that. So for that there is a term used which is known as like a destruction efficiency, which is DE. That's your destruction efficiency is the DE, which is you use as a term of DE. It takes place in the combustion chamber. Then we have another one which is known as the removal efficiency, which takes place in air pollution control environment. So there are the two. So in most of places you will see that people combine these two together and call DRE. So this is DE and removal efficiency is RE. So together it is DRE. DRE is a combination of both. So the required efficiency, so more for most organic compounds we require a efficiency of 99.99%, and for PCBs 99.9999%, so up to 4 decimal places. So we really want it to be removed in terms of the air pollution. So you think about it, so strict air pollution control requirements are there for this waste incinerator. So if you have in addition, we have for SCL, particulate matter and all those things are there. So in one example here, so if you look at PCB, initially the initial values and the outlet value, initial value is what how much PCB is going into the system is provided to us, and in the outlet in terms of what is going to come out of the chimney stack, that's also provided to us. So inlet is 637 kg per hour, outlet is 0.012 kg per hour. So in terms of, we can calculate the DRE will be whatever is the input minus the output divided by the inlet concentration. So input minus output divided by the inlet concentration, and that's multiplied by 100%, to convert that to 100 percent. So we get 99.9 99.9981. So, but that is going to fail. Why it is failing? Because it says for PCB we need 99.9999. So it's less than that. So that means it fails. So we have to improve upon in terms of air pollution control system. So look at from 637 kg per hour to 0.012 kg per hour, and still it fails. So think about how strict we are in terms of the air pollution control. As long as we follow the rules are there, as long as we follow the rule properly, and if we do this, as I've been saying that again and again and again, if we keep our feet correct, waste to energy systems can work in India. The bottom line is keep the feet correct, and is where we fail, where our systems have been failing. And I think we are not paying too much good attention on that side. So energy from waste facilities use high temperature. They do to extract energy from trash, generate electricity, heat or steam, and employ sophisticated emissions control system. Incinerators, that's from the energy from waste facility. If you use an incinerator usually for hazardous waste or biomedical waste, it only reduces the volume of trash and makes it less harmful. Typical mass burn is 1500 tons per day. EFW facility, it produces enough clean renewable electricity for 45,000 homes, which saves around 450,000 barrels of oil each year, and offer net benefits in terms of greenhouse gas. But it has been shown that it emits 2/3 less CO2 than coal-fired thermal power plant. So it's 2/3 less. So it's a lot of, like, nearly more than 60% saving, and emits less than 2/3 less CO2 than oil and natural gas power plant. So it's actually, if you do the life cycle analysis of 1500 tons per day EFW facility, we see that it annually reduces about 270,000 tons of CO2 equivalent emissions. So 1500 tons per day EFW facility reduces 270,000 tons of CO2 equivalent if the things have been going to the landfill. In Europe, we have 400 plants altogether with 60 million tons per year, like 500 tons per day, or this much waste that is being done in Europe. But that's the entire Europe 500 tons per day. In India, we produce much more than that. So there is but in India, if we can keep our feet correct, we can make this waste to energy system works in Indian context. So there is some lost heat, nearly 50 to 60% of the heat is lost. So it can take advantage of lost heat for another process. So it can do that. Local generation station near a facility that needs heat. So if there is the heat can be used, like transport the heat via low temperature hot water, use steam if distance is less than 4 to 5 kilometers. So various fuels can be used to generate electricity: natural gas, coal, wood residue, MSW, biofuels. So those are all used to generate electricity. It captures, this is as part of the cogen, we are talking about as part of the cogeneration. It can capture heat used for secondary processes, for like greenhouse gas operation, paper producing, petrochemical, bioenergy, fuel. So all these you can use, the captured heat can be used in these secondary processes. For example, in a Stuttgart wastewater treatment plant, they dry its sludge and incinerates. They dry the sludge and incinerate with MSW. That produces heat, also heat from anaerobic digestion, and then they use the heat to produce electricity. Then methane gas from anaerobic digestion is piped into the natural gas system. So that's all kind of integrated management system where you can taking advantage of 2-3 different technologies, 2-3 different feeds, and complement each other. So that's how things becomes much nicer in terms of integrated waste management system. Co-incineration waste can also be burned at facilities that are not dedicated to waste incineration. Like for example, mostly it is used for steam and electricity producers, blast furnace, lime and cement kilns. So those are the places where it is used. There are few technical barriers as long as the waste is pre-treated to suit the primary process. The main limitation is the composition of the waste and its possible contamination. So that's we have to worry about. So, composition of the waste and possible contamination it might impact the industrial process. So, those things need to be kept into mind. And then there are other technologies out there. Pyrolysis, it involves thermochemical decomposition of organic material in the absence of oxygen. It's a lower temperature than thermal, so it's 400 to 800 degrees centigrade. So that's the temperature it uses in terms of pyrolysis. Products are pyrolytic oil, gas, and solid char. So, and how they are distributed, it depends on the temperature, and it depends on the temperature of the what kind of whether it's more pyrolytic oil, more gas, or more solid char, whatever is made. So, it depends on the temperature. Oil is used for post treatment. You can use it for chemicals which can extract from the oil. You can use for adhesives. You can use for liquid fuel. So, and then the oil can be combusted to generate electricity. Gas stream contains a variety of gas, like hydrogen or methane, carbon dioxide, carbon monoxide, and those things. Hydrogen and methane can be an important source of energy. Hydrogen, after cleaning, can be used for fuel cells. That's a microbial fuel. Those things are used as well. Further thermal treatment converts hydrogen to methane. So those things can be used, like hydrogen can be used as a fuel. So there are this pyrolysis is done. So pyrolysis, gasification, and combustion, it's in a considered as a separate thermochemical conversion process. However, in a gasification process, you have both pyrolysis as well as combustion does take place. So pyrolysis, what happens is it takes the carbon based material, it have its reaction done with heat in absence of oxygen, and it produces gaseous products, some char, some oil, and those kind of stuff. Char can be used as a fuel. Activated carbon or char oil or char water slurry. The liquid product can be upgraded to refined fuel, added to petroleum refinery feedstock, and all those different kind of. So pyrolysis does help in terms of converting again from waste into different forms of energy. So that's done for that. So in terms of advantages, we kind of talked about that for incineration a little bit earlier as well. It converts solid to synthetic gas, gasification and pyrolysis. It converts solids into synthetic gas. Gas is cleaned before combustion or other uses, and little bit complex technology it is compared to a regular waste incinerator. Plasma is a very high temperature process, total organic destruction, mixed synthetic gas, creates vitrified slag, lowest residual among the different, but plasma requires lots of energy. So it has to be energy neutral, at least if it's not energy positive. But most of the time people are afraid that plasma system will be actually energy negative. So you will be inputting more energy to run the system rather than getting any energy out of it. And that may work okay for hazardous waste or to some extent and also for biomedical waste. For municipal solid waste, since we have so many other options out there, this may not work in a long term unless it's at least energy neutral, or ideally energy like you have more energy coming out of that. So in terms of advanced thermal technologies, the pyrolysis and gasification is there. So you can use as you can see over here, you have the feedstock preparation, then you have gasification and pyrolysis, syngas cleaning, energy recovery, which is you can use it for steam, gas turbine, you can have an exhaust, which is and then for both steam and gas turbine you can generate electricity out of that. So that's you can use it for electricity generation. So what is the pros and cons of these advanced thermal technologies? So what is the benefit and some of the challenges? So pros means few air emissions during syngas. So we have less air emissions coming out, low CO2 is generated into the system, so that's also better. Can be vitrified with some process, recovery of energy from waste, better environmental perception. In terms of pyrolysis, gasification, people have better perception as opposed to going for traditional waste incinerator with all those chimneys. Actually, it's a chimney which creates a lot of things going into the head of people. If you do things properly, the air coming out of those chimney can be very, very clean, actually, maybe cleaner than the ambient air around it, but as long as we meet the air pollution quality standard. Some of the challenges, syngas must be cleaned, so you need to clean the gas, otherwise you cannot, limitation use of is limited. CO2 is formed when syngas is burned. Now when you try to go for vitrification like in plasma arc, high energy requirement and cost is there. Often low energy recovery efficiency than conventional combustion system, so energy efficiency is low. no real environmental advantage over combustion if syngas is used for heat and power. So if you're going to go back and use the syngas for heat or power, it's why don't we go directly for combustion? Because you are essentially you're doing the same thing, doing it in 2 different steps rather than doing it one directly. So here is some like an example of different technologies like conversion technology. We have the pyrolysis, we have gasification, and then these are some of the products. You will have tarts and oil, some gas is there. Then you have extraction, upgrading, synthesis, gas turbine, engine, fuel cells in terms of the energy recovery. Then you have some for the power like chemicals, gasoline, methanol, ammonia. Those things are also used. So those kind of just a so it's in terms of just a like a quick summary of that. So plasma, it's a state of matter created by heating a gas in which certain portion of particles are ionized. Plasma can be created using almost any kind of gas. You can do a nitrogen, oxygen, air. You take to a very high temperature like 200 to 6,000 degrees centigrade. Sometimes it goes all the way to 10,000 degrees centigrade as well. So the plasma system especially goes up to that degree centigrade. Ionized gas is which conducts electricity. Energy is transferred to the waste material. It excites the molecular bond such that the materials is broken into the elemental atoms. When you know elemental atoms, things gets excited, so electrons will go into the higher excitation level, then it will kind of reduce back into the lower excitation to the normal level, and it will release that electron. So all world constituents are completely melted into solid mass called dross, and the minerals can be recovered from dross. All known contaminants is effectively treated like municipal, hazardous, hospital. You see more and more of hazardous waste or hospital waste into plasma arc. You don't see that much in the municipal solid waste unless in some specific cases, maybe some pilot study here and there, but not a single, at least that I'm aware of. If you are, let me know. I don't know any single like a full-fledged big municipality where they are using this plasma arc as the treatment system for treating the municipal solid waste. The process generates PCG, which is called plasma converted gas. Hydrogen fuel is also there as an energy. Large volume of gas requires treatment, so you need to have treatment in terms of large volume of gas is there which requires treatment. Power consumption is 200 to 400 kilowatt hour per ton. So it's double the cost of landfilling but a smaller environmental footprint. So that's what they claim. Of course, we need to find out whether the claim is true or not. So here how it works, the waste feed in goes there, hazardous or non-hazardous. So this is where the things are coming in. It gets heated up at a very high. This is the plasma which is generated from the torch on top, and then things get treated. You have plasma converted gas coming out of that. Then you have some of these vitrified material as a slag. Then the PCG, which is the plasma generated is gas. So you can use it for fuel for electricity generation, fuel for plant, chemicals for plastics, and fuel to product for fresh water, fuel cell electricity. So a lot of things can be done for using this PCG, plasma generated gas. So this is some of the I would say more like an advertisement from these plasma arc companies. You can look at that. This is from the plasma arc company where they are looking at the different components of the plasma arc. This is another sketch essentially from those websites. As you can see on top, that's you can have a plasma arc facility fit there in a traditional incineration, and then we can get rid of many of these stuff which we needed in terms of boiler or cooling tower, back filter, clean gas. Those things can be we don't need those anymore if we can go for a plasma arc. So that's but again, plasma arc is costly, so you need to look at the economics. So let's quickly look over this problem, and then we'll kind of wrap this particular topic. So in terms of if you have to find out the stoichiometric amount of air required for combustion, if the waste formula is given and you have been told how much extra air is like 150 per ton. So you write down this equation, which is the stoichiometric oxidation equation. You find out how much moles. So 1 mole of this will require 8 mole of oxygen. So how much moles are there in terms of 72 grams. So once you know the number of mole, you multiply it by how you will use 8. Like 1 mole of this will use 8 moles of that. So based on that, we find out that all together it comes out to be around 3,556 kg of oxygen per ton. So that's the amount of oxygen that is produced per ton. So sorry, oxygen is required per ton, sorry. And then if you can convert that from oxygen to air, with 23% of air, we know that this much how much will be the air requirement. And from air requirement, we can even go further. This is the air requirement, so that's for per ton. And if you convert that, so this much of air, so how much from this is the kg of air, so in terms of volume of air, we can convert that. So density of air is this much. So therefore, 1 ton of waste requires 11,800 meter cube of air. So so we can use. So that's what it is. This is the other formula. This is the other formula for calculating how much oxygen is required. So we can use a simplified equation, or we can go by step by step at the very like you would do in a simple way. So then you can find out elemental composition for each one, oxygen requirement, how much oxygen is required, the air required from there, excess air 150 degrees and at 150%. So you multiply it by 151.5 to get the excess air. So those things can be done. And for this is another example, you have the organic waste, this much, that's the big formula for the organic waste. We have been given 500 tons per day, excess air is 175%. For efficiency, the plant is working 24 hours a day. So we can find out how much this much 500 tons per day. So this is how much kg per hour. So we get that value in terms of the kg per hour value. Excuse me. So this is our kg per hour value. So this is the how much kg per hour. So mass of molar mass, we can calculate the molar mass because the formula is given to us. So from there we can calculate. So I'm not walking you each line by line. I did that for the biological treatment example. So for this one, I'm expecting you to go through line by line. And then if you have any questions, let me know. Although it's kind of explained in great detail. So you can find out the percentage carbon, hydrogen, oxygen, nitrogen, and sulfur. So you get those. Sulfur has a small contribution, we can ignore that. Then you can use the simplified equation which was shown at the end a few slides back, where you can put this so meter cube per kg of fuel. So that way if you put those numbers, we get that you need 0.8 meter cube per kg of fuel. So and that's so in terms of the oxygen requirement, we can calculate how much oxygen will be required, because we know that 20,833 kg of fuel per hour. So from there we can find out this much, how much meter cube per hour. And once we know meter cube per hour of air for oxygen, we can calculate for air. I'll multiply that 175%, you get that number. And then if ultimately you need to calculate what should be the power of the blower which will blow the air through. So you can use this power equation which is right over there. You can use that power equation and come up with how much you will be requiring in terms of how much is standard cubic feet per minute, the pumps. So or the horsepower, so we get like a horsepower of around 7.6 horsepower is what is needed in terms of for this waste combustor to keep on burning. So another, it's if you look at the wood, so example from C&D debris, you have certain wood which has in percentage carbon, hydrogen, oxygen is given to you. You can find out the volatile solids. So once you volatile solid will be the total minus whatever is the moisture minus the ash. So that will be the volatile solid. Then you can find out the heat value. We get the heat value of around 6,400 BTU per pound, or 14,000, 15,000, nearly 15,000 kilojoule per kilogram. And that kind of the number matches with what is there in the table, in a typical table. BTU per pound we got from DeLong is 6,418, where the paper gives us 6,933. So kind of checks us that it's in the same range. So once we have this, we have to incorporate the water as well. So that will be a that's kind of reduces the BTU value. We can calculate how much will be the heat consumed by evaporation. So we get the actual heat value subtracting that. So that comes down to 6,252. So that's this much of like a heat value coming out for that particular waste. And so then C&D is not pure wood, there will be some metal, there will be some dirt. So we can assume certain percent of contamination, then we reduce the heat value for that. But for this problem, let's work with the pure wood. So use this equation like basic calculation for air requirement, the assumption that only consider oxidation for carbon and hydrogen. Oxygen is when we operate at 50% excess air. Oxygen is there in the waste that will contribute to some oxygen towards combustion. So you can do this air going into this waste and producing these gases out there, with the percentage of wood and all that. So you can calculate how much for carbon, how much air will be required. Again, I'm not going through each, and this step-by-step details calculation has been shown to you, but I want you to walk through the calculation and ask us any question if you have. It should be okay, but just in case. So it's this much kg of carbon, we can find out how much air will be required. Similarly, for hydrogen, we can find out how much air will be required. Then oxygen is already there, so how much oxygen, in terms of the oxygen requirement, how much oxygen is already present in the waste, we can find out those. And then, so how much is required for hydrogen, how much is required for carbon and hydrogen, those numbers are given here, and what is there from the oxygen that has been minus. So this is, and then so effectively we need 385 cubic meter of air per 100 kg of waste. So with that number, we can calculate excess air. With the excess air of 50%, we can find out how much air will be required. And then you should be able to easily solve the exit gas. So we know how much air will be required. So we know this input. If needed, we can calculate all these things coming out from there as well. Like what are the concentration of those things can be worked out. So in terms of the future, the rising, if the energy cost goes up, right now the energy cost is a bit low. Once the energy cost goes up, the waste to energy becomes more attractive. Increasing cost and long-term environmental care with the landfill actually will support waste to energy. So in a country like India, waste to energy has a future. Again, we have to make sure the collection system has to do its job to supply good quality waste material, which has good calorific value, which is should not get diluted from other kind of low calorific value waste material. Energy recovery is recognized as one of the important integral part of waste management. It's a renewable energy. Some countries are also calling it a renewable energy greenhouse gas benefit. European legislation has support waste to energy as opposed to landfilling. So that's and then future challenges, education requirement. We have to get the public on board, increasing the efficiency, finding market for heat, the heat that we are losing. If we can find market, that would be another revenue source. Reducing the operating cost, increasing revenue from the sale of energy. Regionalization requirement to have an economy of a scale. You cannot have a small waste to energy plants. We need the regulator policy support and the acceptance of waste to energy as a renewable energy. So those things will help this particular industry. And I know this video kind of got a little bit over 30 minutes, but we wanted to complete this thermal treatment chapter so that we can move on to landfill disposal. And with this, we complete the discussion on the thermal side. I hope you have a better perspective of the thermal treatment and what are the challenges from the Indian context. And if you are a city engineer, you are a municipality engineer taking this course, or anybody taking this course will be working on this field, make sure our feed is correct. That's the number one message I want you to take it from this particular chapter. For waste incineration, for waste to energy plants, I'm talking from a thermal treatment perspective, to work in Indian context, we have to make sure the feed going into those systems are correct. Technology is well established, it's pretty much and it's being used many places in the world. So there is nothing magic in the technology. It's the feed which holds the key. So with that, let's close this video, and I'll see you again in the next module. Thank you.